All right, folks, welcome back. So last time we looked at the notion of invertible matrix, and we defined matrix to be invertible if you can find another matrix such that when you multiply them, you get the identity, right? Remember that the identity is like the one for matrix product. So we're going to look now at the notion of invertibility and how to determine whether a matrix is invertible or not. So we looked at this example, which I left as an exercise. So we have some matrices which are invertible, some which are not. And our task now will be to try to figure out which are which. So I'm going back to this example from last time. The matrix A2513 turns out that its inverse is the matrix 3 minus 5 minus 1, 2. And how do you check that? Well, if you multiply them together, either direction, you're going to get the identity matrix, which again, for matrices is like the 1 for real numbers, right? So yeah, and I mentioned this result that you only have to check in one direction whether the product is the identity. So formally, a matrix B is the inverse of a matrix A if when you multiply them in one direction and the other, you get the identity. But in fact, it's sufficient to just look at one of the directions. And I gave this larger example of 3 by 3 matrices. So if you multiply the two matrices which are there that you see, you're going to get the identity. If you flip them around, the product will also give you the identity. It's the same result. Okay. All right. So now we're going to look at a very interesting gadget, which is going to allow us to determine if a matrix is invertible or not. So the questions we're investigating are the following. So I give you a matrix A, a square matrix. How can you tell if it's invertible? Now, of course, if you have a candidate for the inverse and you multiply them out, you get the identity, then you know your matrix is invertible. But if you don't have that, how do you know if there is an inverse or not? Okay. Even if you know that a matrix is invertible, how do you find its inverse? I mean, right, you might know that a matrix is invertible without being told what the inverse is. So how do you find it? How do you compute it? Okay, so we're going to look at a gadget. It's a very nice tool, which is called the determinant of a square matrix, and it's a number. So you have a matrix. A square matrix, and from its entries you compute a single number, and which is called the determinant of the matrix. We're going to look, this exists for any size matrix, for any order n, but we're going to look at matrices of order 1 or 2, and I'm going to talk very briefly about matrices of order 3, how to compute the determinant, but it gets a little more complicated. So here is our definition. So I have a square matrix A of order n, which is at most 2. So for our purposes now, we're going to look at matrices which are 1 by 1 or 2 by 2. So the determinant of A is a real number, and you have the notation there for this number, and here is how this is defined. So if it's order 1, so in other words, if your matrix is just a real number, then the determinant is that number. So that's like super easy, okay? For a 2 by 2 matrix, let's say the entries are A, B, C, and D. What is the determinant? Well, you multiply the entries in the main diagonal and you subtract the product of the remaining 2 entries. So if your matrix has rows A, B, and C, D, then the determinant is AD minus BC, okay? So it looks like it's not clear where this comes from. It's not super obvious why this number would be of interest to us, but it is, okay? So I'll try to convince you that this is a very important number. So here's an example. So I have the 2 by 2 matrix 0, 1, 2, 3. It's determinant. How do I compute it? So again, 0 times 3 minus 1 times 2. That's minus 2. So that's the determinant of this 2 by 2 matrix. It's minus 2. If I have the matrix with rows 2, 4, minus 1, minus 2, I compute its determinant. It's 2 times negative 2. Subtract 4 times negative 1. And in this case, it gives you 0. Okay? So if you just take any 2 by 2 matrix, you can, once you've seen the definition, it's easy to compute what the determinant is for any 2 by 2 matrix, right? Okay, now if I take a real number A, and we've again recall that a number or matrix in general is invertible if you multiply it by something else and it gives you the identity. So for real numbers, a number is invertible if you multiply it by some other number and you get 1. So which real numbers are invertible? Well, all of them except 0, right? So all real numbers are invertible except 0. Okay, so here I have a way of rephrasing this. It's sort of silly to rephrase it like that, but you'll see there's a point to this. So a 1 by 1 matrix A is invertible precisely if its determinant is not 0. Okay, so this is just, it seems like a very complicated way to state something that we've known for a while, okay? But it turns out that this is true for matrices of any size, okay? So here is our main important theorem. If you take an n by n matrix, a square matrix of order n, then it is invertible precisely if its determinant is not 0, okay? So that's the test that tells you if a matrix is invertible or not, okay? So to remember this, think of 1 by 1 matrices. It's clear, right? So the determinant of a 1 by 1 matrix is just the entry, that number, and we know it's invertible if it's not 0, okay? All right, so this is not obvious at all right? You're not supposed to look at this and say, oh yeah, sure, that's clear. It is not obvious at all. What I'm going to do is I'm going to show you why this is true for the case of 2 by 2 matrices. So we're going to see why this is true in this case. For, again, I haven't defined the determinant for matrices of size of order n with 3 or more. And I'm going to briefly talk about that, but only briefly, okay? Okay, now to understand what's going to happen, I need this auxiliary result, which is not too difficult to prove for 2 by 2 matrices, but it's a computation. You just basically have to verify that the computation is correct, okay? But this is an important result in itself. If I have 2 matrices, A and B, of the same size, so 2 square matrices of the same size, then the determinant of their product is the product of their determinants. Okay, so the determinant of A times B is the determinant of A times the determinant of B. Okay, so this is, yeah, so important is to notice that this is true for the product, but it is really, really not true for the sum, okay? So it is not true that the determinant of the sum of 2 matrices is the determinant, is the sum of the determinants. This is not true, okay? Never, never use that. This is not true, okay? Notice also that the theorem is clearly true for 1 by 1 matrices, right? This is just, it doesn't say anything very deep, right? It says that A times B is equal to A times B. That's it, okay? For 2 by 2, it's just, again, I said you can verify this by yourselves. There's just algebra, you can verify it, okay? But from now on, I'm going to assume that this is true, okay? So let's see first now why an invertible matrix must have non-zero determinant, okay, using this. So here we go, slowly. This is not too hard. So suppose you have a matrix A which is invertible, okay? So what does that mean? By definition, it means that we have another matrix B such that A times B is the identity, okay? So that's just the definition of an invertible matrix. Okay, so now let's apply our last result. What does it say? It says that the determinant of a product is the product of the determinants, right? So if you look at this equality here, A times B is the identity. It means that the determinant on both sides have to be the same, obviously. And the determinant of A times B, this is the same as determinant of A times determinant of B, okay? Now, it turns out, and you can check this for size 2, it's easy, the determinant of the identity matrix is 1. For any size n, the determinant of the identity matrix is equal to 1, okay? So here's what we get from this, is that the determinant of A times the determinant of B is equal to 1, okay? So I started with any invertible matrix A, and I've got that the determinant of A times the determinant of some matrix B is equal to 1, right? So for sure, the determinant of A cannot be 0. You see, this is clear because if it were 0, you'd multiply by anything and still get 0. So you can't get 1, okay? So the determinant of our matrix A, which I suppose was invertible, cannot be 0. So we've got that direction, right? So any invertible matrix must have non-zero determinant, okay? It turns out that the other direction is also true. So if the determinant is not 0, then the matrix is invertible. So for that direction, I'm going to do it only for 2 by 2 matrices, okay? So this is exactly what I'm saying here. I want to show that if the determinant of a matrix A is not 0, then A is invertible. It has an inverse, okay? So the way we're going to do it, so I'm going to do 2 things at the same time, basically, is to answer 2 questions at the same time, is that I'm going to find the inverse of A for a 2 by 2, okay? So I'm going to find the inverse of A, and if the determinant is not 0, I will show you that this new matrix that I found is in fact an inverse for the matrix A, okay? So here's our result. So I take a matrix A, 2 by 2 matrix, A, B, C, D, and I suppose that its determinant is not 0. Then I claim that the inverse of this matrix is what you see here. So what is that? So it's a 2 by 2 matrix, D minus B minus C A, multiplied by a number which is 1 divided by AD minus BC. Notice that this AD minus BC is precisely the determinant of A, okay? So for this formula to make any sort of sense, this number cannot be 0, right? Okay, so what do? We want to show that this is the inverse. How do you do that? You multiply the 2 matrices and you're supposed to get the identity. That's all there is to it, okay? So let's see, let's multiply, okay? So and again, I mentioned that if you do it in one direction and you get the identity, if you flip the 2 matrices, you will also get the identity. You don't need to check it, but if you want to do it, you can, okay? But it's true all the time. If in one direction you get the identity, it'll be the same for the other direction. So let's see. So I've got a scalar, 1 over AD minus BC times the product of 2 by 2 matrices. So I multiply. Let's see, so I'm multiplying the 2 matrices here again, row times column. So I get DA minus BC, and then DB minus DB, which is 0. Then minus CA plus AC, that's again 0. And finally, minus BC plus AD, okay? So let's see what this is. Now I multiply, how do you multiply a scalar times a matrix, you multiply all the entries by that scalar, right? So I can multiply all the entries by 1 over AD minus BC. So this is what you're looking at here. And you see that this is the identity, okay? Now, I know that following this on slides in a video is not easy. So what you want to do is take a piece of paper, pencil or pen, and just go through it by yourself step by step, okay? All right, so here is an example of what we've been talking about, okay? So I'm given a matrix A, and I'm asked, is it invertible? And if it is, find the inverse, okay? So what have we seen up to now? We have a test to see if a matrix is invertible. You look at the determinant, is it 0 or not? Okay, so I'm going to compute the determinant of this matrix. How do I do that? You multiply the two entries in the main diagonal and you subtract the product of the anti-diagonal. So that's 2 times 5 minus 4 times 3. This is minus 2, okay? Is it 0? No. Conclusion, the matrix is invertible, okay? So that answers the first question. So determinant is not 0, that's it, bingo. We know the matrix has an inverse. Now the last result we just saw tells us, what is this inverse? How do you compute it? We have a formula for it. So it's 1 over minus 2 times a certain 2 by 2 matrix that we saw earlier, okay? So I just replace the values, and this is what I get. So the inverse of A is minus 1/2 times the matrix 5 minus 3 minus 4, 2. Or if you just put in everything together, you get this matrix, minus 5/2, 3/2, 2, minus 1. Okay, and again, you can check it. You can check by multiplying this matrix times A, and you will get the identity matrix. Okay, now I'm going to end these slides by showing you very briefly how to compute the determinant of a 3 by 3 matrix. Okay, oops, sorry. Now, I'm not going to insist on this. So you might see a few exercises, but you're not going to see anything on the test on this. Okay, I'll talk about that next time too. But so that you see at least what it looks like for the 3 by 3 matrix. So there are many ways, many different ways of computing this determinant. You will always get the same answer, obviously, but the methods, the techniques are different. So here is perhaps the simplest way to compute a 3 by 3 determinant. It's called Sarris's rule, or the basket weave method. Okay, so how does it go? So let's say you have a 3 by 3 matrix whose rows are A, B, C, D, E, F, G, H, I. Okay, so you want to compute its determinant. So here's one way of doing it. You write your matrix and you recopy to the right of it the first two columns. So you see in gray here, you have the columns A, D, G, B, E, H, which are the first two columns. Okay, and now you look at the three diagonals going left to right, top to bottom, which are A, E, I, B, F, G, C, D, H. Okay, so these, you multiply these diagonals and you add them up together. Okay, and then you look at the diagonals that are going up, G, E, C, H, F, A, I, D, B, and those you subtract. Okay, so now, of course, you're looking at this and you're thinking, where does this come from? It looks like it's magic. This is not obvious. Okay, so why is that number the one we're looking for? This is like super not obvious. It would take a long time to explain here why that number is the number that tells you if a matrix is invertible, but that's it. Okay, so this is the 3 by 3 determinant. Again, there are other ways of doing it, but this is the most straightforward way, if you wish, to compute it. So here is an example of 3 by 3 determinant. So I'm given a matrix 4, 0, minus 3, 1, 2, 3, 5, minus 2, minus 6. So recopy the first two columns, right? And then you get 3 diagonals going top to bottom. Those you multiply together and you add them together. And then you subtract the upwards diagonals. So this is what you get. So 4, 2, minus 6 plus 0. There's a 0 there. And then minus 3 times 1 times minus 2. And then you subtract those 3 diagonals going up. And the number you get is 12. In that particular example, the determinant is 12. Okay. So it turns out that this matrix is invertible. Now, to compute its inverse is something completely out of the scope of our course, so we're not going to go there. Okay. So that's it for chapter 9. This is the end of it. The last thing I want to say is you might ask, okay, so why are we interested in these inverses of matrices? We're going to see in chapter 10, in the next chapter, that we can solve fairly complicated looking systems of equations using this technique of inverse of a matrix. Okay, so this is one of the reasons that we might be interested in the inverse of a matrix. Okay, so we're going to see this in chapter 10. Okay, so again, this is the end of chapter 9. You have the slides, and we'll see each other next class. All right.